Right, we're continuing our work in Unit 1. The previous things we've looked at had all been review up to this point in time. It's unlikely that you've seen operations with complex numbers. You might have been introduced to the notion of complex numbers in grade 11 math when you were looking at sort of the square root of a negative being a solution to a quadratic and that being a complex number. So I'm going to go through this one in a bit more detail than I did the previous ones because I don't see this as review. I see this as something new. Per usual, we are starting with a Euclid problem of the day, but I'm not going to record the solution to it here. So this one is from 2006. It's a number 3 problem, so it's not a terribly difficult one. Again, solutions are available online, 2 choices. I will eventually move ahead, just quickly show the slide that has the answers, and then through the video you can pause and you can check to make sure your answers are correct. You can pause the video, work on the solution, and then go online to try and find it. And again, it's a really good idea to boost your problem solving and critical thinking skills before you head to university. So the solutions are here. If you want to pause the video, they're also available online. I'm just going to jump right into our math for today. So the square root of -1. So what is the complex number system? It introduces number I with the property I squared is equal to -1. That's going to give us I is equal to -1. This is called the imaginary unit. Just going to write that out. And so if you saw this in, let me just say we're working, we said 2 plus or minus the square root of -4 all over 2. And then this could be written as 2 plus or minus. This could be written as the square root of 4 is 2, and the square root of -1 is I all over 2. And then when you simplify that, you'd get down to 1 plus or minus I. So this is where you might have seen this before, just in the context of solutions to quadratics. We're going to take it a bit further today. So things that once seemed real have now become complex. So let's take a look at what we're doing here. 3 plus 1 is 4, clearly. The square root of 1 is 1. The square root of -1 times -1 is +1, so we could split it apart. And we get the square root of -1 times the square root of -1, but each of those are I. So I now get 3 plus I times I. Of course, I times I is I squared. I squared is -1, so I plop in my -1. I now get that 4 is equal to 2. So what's happened here is that all square roots have 2 solutions, and I have to choose my branch wisely. So really on this line, I should have noted that's 3 plus or minus the square root of 1. And it turns out we are on the wrong branch here. What we should be doing is we're on this branch. So there should be a negative in front of that. If we put the negative in front of that, then it would be minus -1. We'll get 3 plus 1. We'll be back to 4. So you've got to be really careful when you're monkeying around with this, when we're dealing with complex numbers. And remember, of course, the square root of A, B, being equal to the square root of A, square root of B. This going back and forth like this only works for real numbers. And so to make sure that that was going to work, you were told that A and B need to be greater than or equal to 0. You can't split it apart when one of them is negative. And look what can happen. And we can also prove it this way. We have 1 is equal to 1. 1 is equal to the square root of 1. Again, same game, square root of -1 all time, well, both underneath the root. Root all, -1 times -1, that becomes root of -1 times the root of -1. That becomes I times I. That's 1 is I squared, but I squared is -1. Again, what's happened here? When I move from here, I should have had this line in initially, 1 equals 1. When I move from here to there, I should have been noting plus or minus 1. And the root we wanted to include was the negative root. Negative, negative, negative. And then you get negative. Write it off to the side. You get -1, which is 1. So you have to be absolutely careful trying to apply principles and things that worked with real numbers, and real numbers when the radicans were positive, and then trying to apply them in a set of complex numbers. It doesn't work well here. All right, so we're going to solve the following equations in the domain of complex numbers. We are going to have to complete the square. To do that, the quadratic formula is only allowed to be used for real numbers. And we can see what happens if you treat complexities with realism. That's just a little pun intended to just point out here. This is what happens when you treat a complex number as a real number. You can eventually prove things that are not true. 4 is definitely not 2, and 1 is not -1. So the way around this is what we teach you now is we're not going to use the quadratic formula. We're in the complex number set, and I suppose I should have noted that. Z is an element of the complex numbers. So no quadratic formula. We're going to complete the square. We don't have to do completing the square here. What we can do in this particular case is we'll just start by isolating for z squared. So let's do that. We've isolated for z squared. Z squared is -2. Now we'll undo the squaring by square rooting. So we'll get z is plus or minus the square root of -2. I'm going to note that there's 2 possible roots. And of course, this could now be written as the square root of -1 times the square root of 2. And of course, I note that that is I. So that's the next thing we're going to do. Then I'm going to replace this with z equals plus or minus I root 2. No plugging into the quadratic formula when we have complex numbers. So again, this is a complex number. So you're going to start by completing the square. Because we're solving and we have a 0 here, rather than factoring out the 3, we can simply divide everything by 3 and then avoid having to work with fractions when we attempt to complete the square part of it. So let's divide everything by 3. We get z squared plus z plus 1/3 is 0. And now I'm going to need to complete the square in this part. And a reminder that when you complete the square, we're going to get z plus 2 terms, and they have to add to z, so I need a half. So half of 1 is a half. Then I'd have to square that. And then I'd have to take away 1/2 all squared. That is how I will complete the square on just that first little bit. So looking at that, we're going to get z plus 1/2 all squared and minus 1/2 all squared. Well, that becomes 1/4. Now let's just check. Z times z is z squared. Z times a half, and then a half times z. So a half z plus a half z is 1z. 1/2 times 1/2 is 1/4, and 1/4 minus 1/4 is 0. So this is indeed equal to z squared plus z. So we've done that, right? There's our plus 1/3. There's our 0. We're now going to need to clean this little bit up. Maybe get a common denominator. Add those two together. So if we get a common denominator, this is minus 3/12. This one is plus 4/12. Minus 3/12 plus 4/12 is 1/12. So that gets me to here now. And now this is very similar to where we were here. Bring this over to this side. And then, well, let's just do that first. So bring the 1/12 over. So we're going to get z plus 1/2 all squared is negative 1/12. We will undo the squaring by taking the square root of both sides, remembering we have 2 potential roots, just like we did over here. I'm going to get z plus 1/2 is plus or minus the square root of negative 1/12. Then we will bring the 1/2 over next. So we will get z is equal to negative 1/2 plus or minus. And now I decide I'm going to have to clean this up a bit because I really can't leave this like this, the square root of negative 1/12. So the first thing I'm going to note is I need to associate the negative 1 with something. I'm not going to associate it with a denominator because I want to be able to get the I into the question. So I'm going to write this as the square root of negative 1. I can rewrite the square root of 12. That's 4 times 3, so 2 root 3. The reason I'm doing this is because this then can become I. And I'm then going to have to rationalize in times by root 3 over root 3. So now I'm going to have I root 3, eventually getting to 2 times 3, which would be 6. So moving forward, that's what's happening on that next slide. So I've cleaned it up. Again, I'm just going to back you up here to show you. We do associate the negative with that numerator because I want to replace this with I. I'm now going to have to rationalize the denominator, so I'm going to have to multiply by root 3 over root 3. I'm going to have I root 3 2. Root 3 times root 3 is 6. Or root 3 times root 3 is 3. And 2 times 3 is 6. So this becomes plus or minus I root 3 over 6. So plus or minus I root 3 over 6. And then if I wanted to go back to show you, I mean, I would probably be inclined to leave it in this form because on the next slide I'm going to define what complex numbers are. But it's already in the correct form. It's negative 1/2 plus or minus root 3 over 6I. So complex number form, there's the real part, there is the imaginary part. But if you're used to seeing this coming from the quadratic formula idea, if I got a common denominator now, this would be negative 3 over 6. So negative 3 plus or minus I root 3 over 6. But this is probably a better form to look at it because complex numbers we'll see are going to be in the form A plus BI. All right, moving forward. So every complex number can be written in the form A plus BI. A and B are real numbers, so A and B belong to the set of real numbers. I is the imaginary unit where the square root of negative 1 is I. This A is the real part, and I think we should put BI is the imaginary part, not just B. You have to combine it with the I. So BI is the imaginary part. If you want to find the magnitude of complex number, then its distance, its magnitude is defined to be its distance from the origin. Now remember the complex plane, so let me just show you again, because we did this very early on. Let's do 2 plus 3I. So here's the complex plane. I go 2 over in the real direction, and then I go 1, 2, 3 in the complex direction. This is the I-axis, this is the real axis. And now we plot the point 2, 3. So that's how you represent the complex number 2 plus 3I. Its magnitude would be its distance from the origin, and we would have to calculate the length of that. In general, any point on the complex plane, here is AB. Its magnitude would be represented by this. And I could find that using the Pythagorean theorem because the length of this would be A and this would be B. So the magnitude of A plus BI is going to be the square root of A squared plus B squared straight from the Pythagorean theorem. So two terms are interchangeable, modulus and magnitude. How far is a complex number from the origin? So this particular number would be 7 to the right and then 2 down. So a point somewhere around there, that would be 7, negative 2. And then we'd be finding the modulus of that. So you can be in control of timing. I think you could do this one on your own now. You're just going to plug into that formula. If you want more time to do the work, feel free to do so. I'm just going to move forward. So we would say the magnitude or modulus of 7 minus 2i is going to be the square root of a squared. And of course, a is 7 and b is negative 2. So it's 7 squared plus negative 2 all squared. That's going to give us the square root of 49 plus 4, which gives us the square root of 53. So we've just reviewed again that on the complex plane, that's where you can plot. You cannot plot in one dimension. You need 2 dimensions to plot complex numbers. And complex number, let's put something in this quadrant. And let's say this was negative 4 comma 3, negative 3. This would be the complex number negative 4 minus 3i. And its modulus would be that distance from the origin. All right, adding and subtracting. So this is new. You don't know how to add or subtract complex numbers. To add or subtract them, what you do is you add or subtract the real part, and then you can add or subtract the imaginary part. So if I have a complex number a plus bi plus c plus di, the real parts are a plus c. I'll add them together. The imaginary parts are bi plus di. And that in the end is going to give me a plus c, and then I have b plus di. If we're subtracting, we would be a minus c would be subtracting the real parts. And bi minus di would be subtracting the imaginary parts, and in the end my real part would be a minus c, and my imaginary part would be b minus d times I. So a couple of practical examples. You can get started on this particular one. There are the real parts, and there are the imaginary parts. Add the real parts together and add the imaginary parts together. Again, you're in control of the timing. I'm just going to move forward to show you what that would look like. The real parts, 3 plus 7. The imaginary parts, 2 minus 3i. And if we finish, that's going to get us to 10 minus I. So this number is the sum of those two complex numbers. This one will be done similarly, except adding these two complex numbers, we're actually subtracting these two. So again, subtract the real parts and subtract the complex parts. Again, you're in control of the timing. I'm just going to move forward. That's going to be 7 minus 3 minus 3i. Take away negative 6i becomes plus 6i. So 7 minus 3 minus 3i plus 6i. And of course, that's going to give us 4 plus 3i. All right, so adding and subtracting complex numbers is not too bad. What about multiplying? So multiplying, we are going to use the distributive property, and we're going to show you what would happen. So multiplying these two real parts, it's a times c. Then we can multiply these real numbers, a, d, I. Multiplying these real numbers, we'll get b, c, I. And then multiplying these two real numbers, we will get b, d. And I times I will get I squared. That's going to give us AC plus ADI plus BCI, but it turns out that this part here is actually a real part. It's not a complex part, it's a real part, because I squared is negative 1. So I now can replace this with AC minus BD as my real part, and AD plus BCI as my imaginary part. So I'm not going to suggest that you memorize that, but I just wanted to show you what would happen. It seems like when we multiplied them, we were going to get, focusing on that I squared, it looks like we had a lot of imaginary parts. 2 imaginary parts, maybe that one's imaginary, but it turns out you have 2 real parts and you'll have 2 imaginary parts. Right, our first example is not going to be a binomial expansion. It's just going to be a straight distributive property. So you can do that times that, and you can do that one times that. Again, you can be in control of the timing. I'm just going to move forward. So 2i times 2 is 4i. 2i times negative I is negative 2i squared. But I will now replace I squared with negative 1. So 4i minus 2 times negative 1. Of course, that becomes plus 2. So we should be writing this in proper form as 2 plus 4i. The real part first, imaginary part second. There is my complex number in the form a plus bi. All right, in this example here, you're going to multiply them out, but we do know that these are opposite binomials, so I suppose if you wanted to take a shortcut, you could. You could see that you're going to get 16 minus 9i squared. I have probably done the whole entire expansion. Again, you can be in control of the timing. Pause whenever you wish. 4 times 4 is 16. 4 times 3i is 12i. Negative 3i times 4 is negative 12i. Negative 3i times positive 3i is negative 9i squared. Now, that's our imaginary part. This is actually a real part. There's a second real part. I'm now going to replace I squared with negative 1. So I now have my imaginary parts dropping out. 12i minus 12i is 0i. Negative 9 times negative 1 is going to become 16 plus 9. And of course, 16 plus 9 is 25. Again, I showed you with the middle terms, but I said it is possible that we could have just jumped straight to 16 minus 9i all squared, recognizing, of course, that these were 2 opposite binomials. All right, next we want to move into division, but we're going to have to do a little bit of work before we can develop the formula for division. So this is my complex number. Then z with the bar across the top is the conjugate. So z is a plus bi, z conjugate is a minus bi. What I would like you to do is prove that z times its conjugate gives me the magnitude of z all squared. So that's going to be a bit of a proof. I'm going to suggest you just start with z times the conjugate of z and see if in the end you can prove that that's the magnitude of z squared. Again, you can be in control of the timing and pause whenever you wish. All right, so working through this, z times the conjugate of z is a plus bi times a minus bi. We've learned how to expand that. We should get a squared minus abi plus abi minus bi squared. Or, we could jump directly to that because they are opposite binomials, but I did all the work for you. That is going to be 0. And of course, I'm going to replace I squared with -1. So I now have a squared minus b squared times -1. That becomes a squared plus b squared. But we did learn on a previous slide, let me just come back to this, like what is the magnitude or the modulus of, so we went like this, we want to find the magnitude or modulus of a complex number. So this is a plus bi. We said from the Pythagorean theorem that the modulus of z would be the square root of a squared plus b squared. That's coming from the Pythagorean theorem. And now z squared, of course, the modulus of z all squared, would simply be a squared plus b squared, which is what we have there. So down to there. And just showing you that the modulus of z, of course, would be the square root of a squared plus b squared. And then I'd square that. That would get me to there. And of course, that little bit being the modulus of z. Now, what's that going to give us? If we take this equation here and we rearrange it, so take this equation, rearrange it, simply by moving the z over here, so we'll get 1 over z on this side. We move this to that side, and we will get z conjugate over the magnitude of z squared is equal to 1 over z. So whenever I see 1 over z, I can replace it with this formula. And you see we're going to use that in a few minutes to develop a formula for how we're going to handle it when we want to divide two complex numbers. So I want to divide two complex numbers. So z divided by w could be written as z times 1 over w. But we've just proven this little formula over here that we could replace 1 over w with the conjugate of w times the magnitude of w squared. So let's come back over here and see that's just what we did. We replaced 1 over w with the conjugate of w over the magnitude of w squared. Now let's back up a bit and come back over to this slide. We've also proven that the w times its conjugate is the magnitude of w all squared. So we then can come back over to here and we can replace the magnitude of w squared with w times its conjugate. So in the end, this is where we are. We have z over w would be the same as z over w times the conjugate of w over the conjugate of w. So that's exactly what we're going to do when you want to find the quotient. What you're going to do is multiply the numerator and denominator by the conjugate of the denominator. So in this case, 2 plus I over 2 plus I. So that's what we're going to get going with. Again, you can be in control of the timing. I'm just going to move to the next slide. So multiplying by the conjugate, we're going to get 3 over 2 minus I times 2 plus I over 2 plus I. And then I will multiply these out. That's going to be 6 plus 3I. And I suppose we could just jump to 2 minus I squared. We're going to get 2 plus 2I minus 2I minus I squared. I'm just jumping now straight to 4 minus I squared. Now 4 minus I squared is going to be 4 minus -1. So 4 minus -1. That's going to give us 6 plus 3I over 5. There's 6 plus 3I over 5. And now we'll split these apart. That's 6/5 plus 3/5 I. 6/5 plus 3/5 I, and there is our complex number. So you see how if we divide those two complex numbers, this is complex, but it absolutely was pure real, and we divide that by a complex number that has a real and imaginary part, it has produced a complex number with a real and an imaginary part. So again, the key when you divide two complex numbers is to multiply by the quotient, I guess, of the conjugate of the denominator. So we're going to multiply by W conjugate over W conjugate. All right, time for the next example. You can pause whenever you wish. You're in control of the timing, but the conjugate, we should be doing I minus 1 over I minus 1. So I'm going to move on to the next slide. 7 plus I over I plus 1 times the conjugate of the denominator, I minus 1 times I minus 1. That's going to give me 7I minus 7 plus I squared minus I. And the denominator is just going to be I squared minus 1. So there's the 7I minus 7 plus I squared minus I. We're just I squared minus 1 here. And we're going to have to clean up now. We could do 7I minus I is 6I. That's negative 7 plus negative 1 minus 1. So there's the 6I minus 7 plus negative 1 minus 1. That's going to give us 6I minus 8 all over negative 2. So 6I minus 8 all over negative 2. And then we're going to divide. We're going to get positive 4 minus 3I. So positive 4 minus 3I. So when we divide these two complex numbers, notice it returns a complex number. All right, so I've covered the operations. I know they were new. They're not too bad. We now know how to add and subtract two complex numbers. We know how to multiply two complex numbers, and we now know how to divide two complex numbers. And the division of two complex numbers really reminds me an awful lot of trying to rationalize the denominator. Say, well, we were doing stuff like this, root 3 plus root 8. Sort of a similar technique. It creates a number equivalent to this number in which the denominator is a rational number. When we do this here, it creates a new complex number, if you like, in which the denominator was a real number. And then we could split it out. All right, so the next thing we're going to think about now, bit of an activity for what are fractals? It turns out this is a beautiful fractal here. Fractals are created in the complex number system. So what is a fractal? It's an object that displays self-similarity on all scales. Fractals can have a fractional dimension. Fractals are formed by an iterative process. So what's happening in this case? So this particular case, this one is Sierpinski's triangle. In this particular case, what happens is you split this into 3 equal pieces. This is an equilateral triangle. And then you draw an equilateral triangle off that side. So you split this into 3 equal pieces, draw an equilateral triangle, and you do that here. So that will create this shape. Then you have to repeat that. So now you're going to split this side into 3 equal pieces, draw an equilateral triangle on all of those little segments you get to here. And you keep repeating that process, and then you get to this one here. Now this is called Koch's snowflake, this particular one. This is the similar idea, but sort of done off of a hexagon, where you're drawing like sort of a trapezoid off of there, or half of that hexagon. In Sierpinski's triangle, what you do is you split this into 4 equal triangles, and then you anti-shade. I guess I'm going to call that the middle. Then you do that for this one. Create your 4 equal triangles, and then sort of anti-shade the middle one. Anti-shade the middle one, and so on and so on. And then you get something that looks like this. So moving forward, I'm going to talk about the Mandelbrot set. So what is the Mandelbrot set? It's a set of complex numbers for which this function, so we're going to define it, f at z is z squared plus c, remains bounded when iterated starting at a z of 0. It's called the orbit of the seed of 0. So we're starting with the seed of 0, and we're following the orbit. So let's consider a c of 1. So we're starting at 0, z is 0. We plug in a 0, we get 0 squared plus 1 is 1, and then we repeat that. We now plug a 1 in and back into the equation. So notice it's like a composition of functions. Plugging the 1 back into here becomes 1 squared plus 1, which is 2. Then plugging the 2 back into here, we get 2 squared plus 1, which is 5. Plugging the 5 back in there, we get 5 squared plus 1, which is 26. This is shooting off to infinity, right? It's just going to keep getting larger. This tends to infinity, so c equals 1 is not in the Mandelbrot set. And in fact, we're looking for, once you hit 2, you're shooting off to infinity. So it's called escaping. So we're escaping. How many times did we have to do that? We did that twice, right? So it escaped after 2. Let's consider I. So when we plug in an I, we're going to look at this being z squared plus I. So the I, because we're testing a C of I now. Remember, we start with a seed of 0, so we're going to start with z being 0. We're going to get 0 squared plus I is I. We'll now plug in an I. We're going to get I squared plus I. I squared is -1, so it's -1 plus I. Coming back over here, plugging in -1 plus I in for z, and then adding. We're testing I, a C of I, plus I. This is going to give me +1 minus 2I plus I squared plus I. 1 plus I squared is 0. -2I plus I is -I. So we're back at -I. Then when I plug in -I in there, I'm going to get -I all squared, which is I squared plus 1. And now I squared is -1. So -I times -I is positive I squared. Positive I squared is -1. We're at -1 plus I. Now we're going to cycle. When I plug that back in, I'm going to get to -I, and so on. So eventually this orbit cycles. It has a period of 2. So C equals I is part of the Mandelbrot set. Now I'm going to jump forward and show you the Mandelbrot set. Anything shaded in black, anything that's black is part of the Mandelbrot set. Anything else in a different color isn't part of the Mandelbrot set. It ends up being graphed on the complex planes. Again, as I mentioned, the points colored black are part of the set. If a sequence has a term greater than 2, that's what I've mentioned, it will escape and grow unbounded right here. That's why this escaped and grew unbounded. We can track how many times or how many terms it will take to reach the number 2. So in this particular case, it took 2 terms to reach the number 2. So everything that would take 2 terms to reach 2 will be now shaded in one color. So perhaps that color blue is terms that are numbers that took 3 terms to escape. So that's what I'm noting here. Points that escape are colored based on their escape time. So all of these things in this shade of green have the same escape value, whether that be 2, 3, or 4, maybe 5 or 6 terms before I actually escaped. Now I'm going to jump over here and show you. Here is the Mandelbrot set plotted on the complex plane. There is our imaginary axis. Here is our real axis. So we did say that the point I, when we were at I, would be in the set. So, and we said that the point, let's just jump back over here. So when we do C equals I, so that's 0 plus I, that is in the set, and 2, 0 isn't. So let's come back over here. So 2, 0 is over here somewhere. That's not in the Mandelbrot set. I is in the Mandelbrot set. So somewhere along this axis, we're intersecting right there. So 0, I is in the set. Or that would be 0, 1, not 0, I. So this is what the Mandelbrot set looks like. And then you're going to use the Mandelbrot Set Explorer found at the link below. You can change the colors and zoom in. I'm just going to show you what that would look like. So if I click on this, it'll jump over to here. So this is actually what the Mandelbrot set looks like. I'll give you perspective again, just so you can see roughly where the axes would be positioned. So halfway this way, we do have symmetry sort of this way, is the real axis, but we're just to the left of this little bubble here is the imaginary axis. So the imaginary axis is somewhere over here, the real axis is here. And then what you're going to do is you're going to create a piece of artwork. Now the way this works is if you draw a grid, it zooms in on that grid. And I'm not sure how long this is going to take. There we go. See how there's sort of self-similarity? I zoomed in on that bubble and I get another bubble. So let me zoom in over here. And then I'm getting another bubble. Let me zoom in here. And now the shapes are sort of flattening out a bit. Where do I want to zoom in? Somewhere here. And then you find sort of an image that speaks to you, and then you can change the colors on this. So I can come over here and I can click there double click in there, and maybe I want to make that red or something. Then maybe I want to double click over here. Maybe I'm going to change this one for a second so we can be clear what's in the Mandelbrot set and what isn't. So I'm going to change that to sort of a greeny color. Now all our darker colors here, this one being on this end, is definitely in the Mandelbrot set. And then if you want to add some more colors, you can change that to maybe something different. And then when you get a piece of art that you're happy with, then what you can do is you can just save it. And then the quality, clearly, like the man is saying, ridiculous, that that would be so big, so large, you probably would not be able to fit it on your computer. So once I say, well, maybe I'm happy with 4, I would then save the image. And then it's going to put it on my staking time. And that's why I said it would be ridiculous. And then I can view it. And then I can save that. And then I can use that to create a piece of artwork. So I'm going to show you over here that I created this using that Mandelbrot Set Explorer. And I'm noting the path to learning is never straight, which is absolutely 100% true. It isn't straight. So I've got some interesting curves here. And savor the intrinsic beauty in the process of learning. So it seems like you're struggling, but in fact, it's a fascinating journey to higher learning. And then on the bottom, I've added the cautious seldom err. That's what Confucius said. So I say throw caution to the wind because that's the only way you can learn, by making lots of errors. So what you would be doing is you'd be creating a similar poster, putting some words on it. You could dump this into, I'm going to say Word to do this, and then you'd be creating a poster. And then what we would do is eventually you would post them. Now these are the ones from the last time I taught this course. So here are the interesting posters that other students created. And again, that would be graded out as some marks and counted towards your grade. All right, so that brings us to the end of this lesson. This lesson was all about operations with complex numbers. You're now an expert on adding, subtracting, multiplying, and dividing complex numbers. And you've learned some pretty fascinating things about fractals, and you're ready to make your own fractal poster. So again, thank you for your support. Don't forget to like and subscribe. And as always, do take care.